I hope by now that you have downloaded our free simulator program from this website. It will make it much easier to follow the tutorials as we continue. To gain the full benefit of the tutorial, you should use the simulator to experiment with circuits of your own. We concluded part 1 with Ohm's law. Using the simulator, you can verify Ohm's law for a variety of voltages and resistance, or you can try it out with real components if you have them. Let us compare a circuit with a single 1K ohm resistor with a circuit containing two 1K ohm resistors in series. In series simply means in line. We would expect that if one resistor restricts the current, then two similar resistors would restrict the current doubly. Testing the circuit, we see that this is so. In the first case, the current is 9 milliamps, and in the second, it is only 4.5 milliamps, which is half the current. We should mention that a milliamp is 1,000th of an amp. A microamp is 1,000th of a milliamp. A nanoamp is 1,000th of a microamp, and a picoamp is 1,000th of a nanoamp. Therefore, a picoamp is 1/1,000,000th of a millionth of an amp. The terms milli, micro, nano, and pico occur in other places as well. Also notice the special mu character for the micro symbol. So when resistors are placed in series, the total resistance is simply the sum of the individual resistances. Now let us see what happens when we place two 1K resistors in parallel. The single 1K resistor allows a current of 9 milliamps, while the resistors in parallel allow a current of 18 milliamps. We see that the current has doubled. This should not surprise us. If we return to our water analogy, we see that we have provided a second conduit for the current to flow. We have seen that in general, current is inversely related to resistance. If the resistance is small, the current is large, while if the resistance is large, the current is small. We could therefore describe the conductivity of a resistor as the inverse of the resistance. When we have resistors in parallel, we can say that the total conductivity is equal to the sum of the conductivities of each resistor, as we saw with the water analogy. In mathematical language, the reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistors in parallel. You can show that this formula is correct using an ohm meter with various combinations of resistors. You can also test various combinations of resistors in series and in parallel and see if you can predict the total resistance. The voltmeter measures voltage. Whereas an ammeter measures current passing through it, a voltmeter allows no current through it. The voltmeter is able to detect the difference in voltage between 2 points. This is called the potential difference. In this example, the voltmeter detects a potential difference between the positive end of the battery and the negative end of plus 9 volts. We could say that the voltage at the positive end is plus 9 volts and the voltage at the negative end is 0 volts. Because the top of the resistor is joined to the top of the battery, we can also say that the voltage at the top of the resistor is plus 9 volts. Similarly, the voltage at the bottom of the resistor is 0 volts. In this example, we have resistors of 3,600 ohms and 1,200 ohms. We have a 6-volt battery and have placed 3 voltmeters. Current is flowing through the two resistors. The drop in voltage over the two resistors is 6 volts. We see that the voltage drop over the 3,600 ohm resistor is 4.5 volts, while the voltage drop over the 1,200 ohm resistor is 1.5 volts. We say that the two resistors have acted as voltage dividers. The voltage drop over resistors in series is proportional to their resistance. You can test this with various resistors. Also, see if you can calculate the current flowing in each resistor using Ohm's law. Here we use the voltmeters to test various configurations of batteries. In the first case, we see that if we place batteries in series, the total voltage is the sum of the individual voltages. In the second case, batteries in parallel do not deliver higher voltage, but the batteries should last longer. In the third case, we see what happens if we place two ordinary batteries of unequal voltage in parallel. The voltage delivered is the higher voltage of the individual batteries. We turn our attention to diodes. On the left we have a standard diode. In the middle we have one we have already seen, a light-emitting diode. On the right is a signal diode useful for radio reception. You may notice a silver band at the left-hand end of the standard diode. This indicates the cathode or negative end of the diode. The light-emitting diode has a flattened edge next to the cathode lead. The signal diode has a black band at the cathode end. Knowing which is the cathode or negative end of the diode is very important, as we shall see. The opposite end from the cathode end is the anode end or positive end. In this circuit we have two diodes. When we switch on, the LED lights up as expected. But what happens if we switch one of the diodes around so that the cathode end is connected to the positive end of the battery? Rotate the diode. Run the simulator and switch on, and no current flows. This is the valuable feature of a diode. It allows current to flow in one direction only. One use of a diode is to protect a circuit in case the battery is connected the wrong way around. Initially the diode was developed for rectification of radio signals. More about that later. Atoms bond together to form molecules. How they bond is determined by their valence electrons. Atoms with free valence electrons are apt to bond with other atoms also having free valence electrons. The hydrogen atom has one valence electron, so two hydrogen atoms bond together to form a hydrogen molecule. The hydrogen molecule is stable because the valence electrons are employed by the bonding process, so there are no free valence electrons. A semiconductor is a material which is somewhere between conductors like metals and non-conductors like wood. An example is silicon. The silicon atom has 4 valence electrons, and in a pure silicon crystal, these electrons are employed in bonding with neighboring atoms, so there are no free valence electrons. Phosphorus has 5 valence electrons. If this is added to silicon as an impurity, 4 of these will bond with silicon, leaving 1 electron free. There will be many such free electrons, and as they are negatively charged, we call this substance an N-type semiconductor. It has negative charge carriers. On the other hand, boron has 3 valence electrons. If this is added to silicon as an impurity, these 3 will bond with silicon, leaving a hole where an electron would have been if the atom had been silicon. These holes are positively charged, so we call this substance a P-type semiconductor. It has positive charge carriers. Now we can show how a diode works. P-type and N-type crystals are fused together. Electrons can be drawn from the N-type semiconductor through the holes in the P-type semiconductor towards the positive end of the battery. All the while the electrons in an N-type semiconductor are replenished from the negative end of the battery. Current flows through the diode. What happens if the diode is rotated? The free electrons in the N-type semiconductor are attracted towards the positive end of the battery, and the holes in the P-type semiconductor are attracted towards the negative end of the battery. The result is that there are no charge carriers at the junction between the crystals, so no current can flow. Now we put an ammeter in the circuit with a diode and a 1K ohm resistor. We switch on and see that the current is 8.3 milliamps. What has happened here? We have a 9-volt battery and a 1K ohm resistor, so we would have expected a current of 9 milliamps. The answer lies in the diode. The diode has a so-called forward bias which acts like a negative voltage. The external voltage must exceed this bias for current to flow. This is called its threshold voltage. The threshold voltage of the simulator diode is 0.7 volts. So the current is 9 volts less 0.7 volts divided by 1000, giving 8.3 milliamps. Try this circuit with a 0.6 volt battery and you will see that no current flows because the threshold can't be reached. That concludes part 2 of the electronics tutorial. In the next part we will investigate capacitors.